Hello everyone, I am Balaji Rajashekharan and this is my project presentation for wireless communication EEL 6509. The title of my project is Wireless Orthogonal Frequency Division Multiplexing Systems Channel Estimation. This is the overview of this presentation. These are the topics I'll be covering for the next 10 minutes. So I'll be starting with the objective, followed by the introduction about the OFDM system. That is followed by the advantages of the OFDM system, and then I'll discuss the usage of the wireless OFDM systems in various domains, and later I'll present a block diagram describing the OFDM system and explain step by step about the OFDM system's modulator and demodulator. Then I'll explain about the channel estimation, and I'll be discussing the block type and the comb type palette insertion techniques. That will be followed by a discussion on the LS, MMSE and LMMSE estimators. That is followed by a MATLAB demo and simulation I will be showing in MATLAB. And then comes the results and analysis, followed by the conclusion. Objective. The main objective behind this project was to study the wireless orthogonal frequency division multiplexing technique, its working and its advantages. To implement channel estimation using block type pilot insertion technique in MATLAB, and to obtain the simulations and analyze the results. Introduction. As we all know, FDM stands for frequency division multiplexing. Most of the FDMs are orthogonal in nature, but OFDM is reserved for a special type of FDM technique we will be discussing in this project. In OFDM, all carriers are orthogonal to each other. OFDM is a type of FDM technique where a signal is split into several narrow band channels at different frequencies. It uses a large number of carriers spaced apart at different frequencies to facilitate effective digital transmission. Advantages of OFDM system. So OFDM systems have the ability to handle severe channel conditions like interference, fading and attenuation without complex equalization filters. It is also effective in multipath propagation as it is robust to intersymbol interference and fading. OFDM systems also boast of a very high bandwidth and bitrate transmission capability. So this is a conventional FDM system and this is an OFDM system. We can see that the OFDM system has a high bandwidth and bitrate transmission capability, and this facilitates a lot of bandwidth saving. We will continue with the advantages of the OFDM system. OFDM system effectively handles intersymbol interference and intercarrier interference in single and multi-carrier systems respectively. It can be easily implemented using FFT technique, that is fast Fourier transform. Moreover, OFDM systems are less sensitive to timing errors. Usage of wireless OFDM system. Wireless OFDM systems are widely used in wireless technologies. To name a few, we have the wireless LAN, WiMAX, mobile phones, and also 4G is a wide user of the wireless OFDM system. OFDM systems are also used in digital radio and digital TV systems. It's also used for power line communication, and it is used in cables such as multimedia over coax cable, popularly known as EMOCA, ADSL and VDSL as well. This is a block diagram of OFDM system. So this explains the flow of data from the transmitter to the receiver over the channel in an OFDM system. So we basically have a binary data source code that is received by a signal mapper and sent into a serial to parallel converter. So this portion of the block diagram is called as the OFDM modulator. So once the signal is converted to parallel, it is passed through a pilot insertion. So we use a block type pilot insertion in our project implementation. After the pilot insertion phase comes the inverse fast Fourier transform phase. So the modulation of a signal takes place here, and this is followed by a guard interval insertion. The insertion of guard interval helps in eliminating the intersymbol interference and the intercarrier interference during the channel transmission. So this is followed by a parallel to serial conversion, and that is sent to a digital to analog converter and a low pass filter and sent through a channel. And from this channel, at the receiver's end, we have a analog to digital converter which converts the signal, and it is sent to a serial to parallel converter. So this portion of the block diagram is called the OFDM demodulator. So basically we are removing the guard interval here, which we inserted in the modulation section, and then it is sent to a FFT. So that is the fast Fourier transform. And then this is followed by a signal correction based on pilot, and once the parallel signal is out of the demodulator, it is again converted. A parallel to serial conversion takes place, and the output is taken out to a signal demapper. So this is the basic working of an OFDM system. Channel estimation. Channel estimation plays an important part in an OFDM system. It is used for increasing the capacity of the OFDM systems by improving the system performance in terms of bit error rate. Pilot-based channel estimation is basically of two types. So one is the comb type, and the other one is a block type. Block type and comb type pilot insertion. So this figure gives a broad idea about the block type pilot arrangement and the comb type pilot arrangement. So in case of block type pilot arrangement, all the subcarriers are used as pilots in specific periods, which we can see here. So these filled in dots are the pilots, and the unfilled dots are the data. In case of a comb type, only part of the subcarriers are reserved as pilot for each symbol. As we can see in this diagram, only some of the subcarriers are reserved as pilot. LS, MMSE and LMMSE estimators. LS basically stands for least square. It is a method of estimating by minimizing the square difference between the obtained data and the expected values. MMSE stands for minimum mean square error. It is a method of estimating by minimizing the mean square error, which is usually a measure of quality of an estimator. Linear minimum mean square error. It's a simpler and it retains the MMSE criterion. The constraint in this estimator is that it is assumed to be linear. Let's have a MATLAB demo and simulation of our project. So first I'll show a demo that gives us a plot of the signal to noise ratio versus the channel MSE, that is the mean square error. So now I'm giving a channel length of 5 and I'm running the code. So this is the plot obtained. So in this plot we have the least square MMSE, time domain LMMSE and frequency domain LMMSE. We also have the theoretical value of the LS and LMMSE techniques, which is described by the dotted red line and the dotted black line here. So it is basically used to show the difference between the theoretical value and the obtained value. So for this channel length of 5, we can see that the theoretical and the obtained value are overlapping each other. It's the black lines here and the red lines that are overlapped here. So now let's change the channel length to 40 and see how the simulation turns out. So this is a simulation for a channel length of 40. So we have the signal to noise ratio here and the channel MSE here. So as we can see, the deviation from theoretical value and the obtained value has increased a lot. So this is the theoretical LMMSE value and this is the obtained LMMSE value. And this is the same case with LS2. This is the theoretical LS and this is the obtained LS. So we can see as the channel length is increased, the deviation between the theoretical and the obtained value is also increased. Now let's perform another simulation that gives the relation between the signal to noise ratio and the symbol error rate, whose details are explained later in the presentation. So now let's run this code. And this is the plot that we get for the signal noise ratio to versus the symbol error rate. So the explanation of these plots are given in the latest section of the presentation, which I'm going to continue now. Yes, the result and analysis. So as I showed you, the first plot was the signal to noise ratio versus the channel MSE. So this is the plot that we obtained for the channel length of 5 units, and this is the plot that we obtained for a channel length of 40 units. So as I explained before, for lesser channel lengths, the difference between the theoretical and the obtained values is negligible. So we can see that theoretical and obtained values overlap each other. But in case of channel length of 40, the deviation from the theoretical and the obtained values is more. So as we see, this is the obtained value and this is the theoretical value, and they are nowhere near each other. And moreover, the plot also implies that the MMSE technique is far more better in performance than the least square technique. Another factor to analyze the LS and the MMSE estimators is the SCR. SCR basically stands for symbol error rate. It is the ratio of the symbol errors to the total symbols sent. So basically, if the SCR is higher, it implies a poorer quality in the communication. So this is the plot we obtained for the SNR versus SCR, and the black line with the dot with the triangles is the one for MMSC, and the blue one is for the LS. So as we see, for all values of SNR, the MMSC's plot is always lesser than the LS. So this again proves that MMSC is better than LS in terms of SCR2. So from this project implementation and the simulation results we obtain, we can conclude that from the plots of the SNR versus channel MSC, the MMSC performs better than LS for all the channel lengths. So moreover, the deviation of the obtained values from the theoretical values increases with the increase in the channel length. From the second plot, that is the plot for the signal noise ratio versus the symbol error rate, we have the MMSC has a lesser symbol error rate for all the values of SNR. So this again proves MMSC is better than LS even in terms of signal error rate. The only drawback of the MMSC is that it is complex to implement compared to the LS estimator, but still MMSC performs well when compared to the LS estimator. Thank you for watching the presentation.